Welcome to another coding session where I'm creating a new programming language called Plum. It's on GitHub, kind of looks like this, and yeah, before we get started I kind of want to reflect on the last coding session because that didn't really feel productive, at least the second half of that. So maybe let me switch to my iPad. Okay, so basically our compiler pipeline is quite long already. We start with the source code that gets converted into a tree of the lines according to the indentation. That's called bacon. That gets passed into a tree representing the syntax. That gets converted into a graph of expressions, and that gets type checked. And finally, well, we did something below that. Yeah, so initially we compiled just to C code and then let the C compiler take care of the rest. That works, but in the long term I wanted to have a bit more options. For example, I want to allow to compile code on the fly while the program is running. So in the long term, the C backend should be replaced with an interpreter. And that's exactly what I did. I replaced this with an interpreter. The interpreter was quite high level though, so it had basically instructions like create a new object, create a new struct, create a new enum value, access the member of this struct. And in the last session, I replaced that high-level interpreter with one that's more low-level. Basically one that operates only on bytes. And that didn't go as well as I would have hoped. Right, so why not? Turns out these stages right here. Why do we even have these stages in the first place? We could just go from source code to something low level directly. And the reason is that doing all of this work at once is just a lot of complexity for us humans to keep in mind. If we read some definition in the code, then what machine code do we emit? Like that's so far removed from what we think about. And there were some compilers that work that way, that just scan the source code, and while they do that, they immediately can emit code, like machine code. These are often called single pass compilers, and for example C does that. That's the reason that you have to declare a C function before you can use that. Yeah. But this is very impractical. And basically this gap in the end got too big, I think. So down here at the bottom, we have the yogurt, which is a type-checked version of a program. And we converted that into, first into C code, which was quite easy, like I think 200 lines or something. Not a lot of complexity in there. When we replaced that with an interpreter, this was a lot more complicated because the interpreter is stack-based. So we have to turn this graph-based, type-checked representation of our program into a stack-based representation that is fit for execution through some virtual machine. And that conversion from something expression or graph-based into something stack-based takes a lot of mental overhead, I think. Like this is something that's difficult to reason about and to think about for us humans, And then when I tried to turn this stack-based interpreter from working on an object level to working on individual bytes, I added this additional complexity for converting high-level data structures into like low-level memory layouts and memory operations. So this compiler stage right here, this got really, really difficult, and it had a lot of complexity inside of that. And yeah, basically at the end of the session, I figured out that it makes sense to add another compiler stage. A compiler stage that doesn't have types anymore. Like all of the types that are present in here, they disappear, and instead it only operates on memory. Something. I don't know how to call that. And yeah, the transformation to code that is stack-based would then happen in another compiler step. Yeah, that was basically the last, I think, 10 minutes or 20 minutes of the last session. Basically me realizing that, hang on, I'm basically stuck writing this huge, complicated compiler step. And it is really, really difficult to reason about. And yeah, I wish I could have done that a bit sooner, but I think it's important to realize that there is a trade-off between adding compiler stages and removing them. Adding a new compiler stage means that the overall complexity of the compiler gets bigger, because, well, now you need to understand more concepts and there is just more code. But the individual steps of the compiler, they get a bit simpler, because you can basically divide these actually difficult to think about complex parts into separate regions and only tackle one problem at a time. Yeah. So basically that's the reasoning behind the new compiler stage that I began designing at the end of last session. And today we're going to continue with that. Like design the compiler stage and then implement the compilation from that compiler stage to bytecode and from the typed representation to that compiler stage. Okay, I came up with this. Yeah, this is a compiler stage that is expression-based, similar to the previous stages. But most expressions, expressions can be nested. Unlike in the previous compiler stages, where we only have IDs that we pass around. And for example, when we want to create a struct, really we first create expressions for creating the field values, and then we have this struct operation that combines all of those fields into a struct. In here, that's not the case. In here, expressions will match. We don't have struct expressions here, but if we had some, then it would basically look like a struct, and then the field values, they are calculated directly in the struct instead of like having these temporary variables before. Right. So if these things right here, they don't have types, so they are not values, semantic values of our language, then what are these? I think each expression here is just some memory, aka something with a size and an alignment. Alignment is a concept I introduced in the previous session. That's basically just that some read and write operations on memory are more efficient if the memory address is divisible by some number. So for example, integers, reading them and writing them is more efficient if the address is divisible by 8 bytes. Right. So the idea here was that we have these expressions, which are just some memory regions. And for example, having an enum, like the maybe enum, which is either sum with an integer in this case, or none. Instead of representing that as something typed, we would just have these things. So basically the curly braces mean this is multiple things in memory next to each other. And in this case, that is the sum case. So that is the 5 and then the byte 1, indicating that this is the sum variant. And the none variant, like this other branch, must have the same memory layout, like the same size and alignment, but it may contain different content. And then, you can see in this case, the padding here is, we have this padding of 8 bytes, because we don't have a number to store here. And we have a 0 at the end, which indicates that this is the none variant. Okay. I guess let me just refactor a few of these things. So I said that expressions, they each should have a size and an alignment. And I think I'll model that here explicitly. So I am going to have, I don't know, some enum, and the expression will be a struct that contains this enum as well as a size and an alignment. Okay. Yeah, I won't care too much about those down here. Oh yeah, also choosing a name is difficult. Low-level intermediate representation is a bit boring. It is, it makes sense. But I think I'm gonna rename this to Waffle, which is, hang on. So this has alignment and all of the memory layouts for the types. So this is a well-aligned form of fixed layout expressions. Beautiful. Going, following the patterns of using breakfast names as compiler stages. Yeah, I'm also gonna adjust that here, so yeah, we have this extra compiler stage now, the waffle. Yeah, let's also add that, I guess, here. And yeah, the waffle should add imports the main file, that's also nice. Yeah, so then let's rename these. And maybe add printing, because that should be an easy task, just to get me started, to get me into coding, and then tackle more complicated things. Yeah, so writing waffle means that we basically want to write all the functions, which is pretty similar to what we did in the yogurt. Yeah, functions have a key, which is a waffle signature, and the actual function. Beautiful. And then for the functions, yeah, the signature just wraps a string. Perfect. And let's actually call that string out still. Doesn't fit on one line, but that's fine. And that rhymes. Right. Yeah, writing the actual function. Hang on. I'm gonna zoom in a bit. Oh yeah, we don't have a yogurt body, do we? No, we do have a waffle body. Okay, sure. Yeah, bodies don't have parameters in here. instead they can just directly reference these local IDs from outside of the function. And also in the yogurt, bodies were used for switch bodies, and basically you could get the payload of enums, but in here everything is just memory anyway, so you can just access that particular part of the memory. Okay, so we have the body locals, or what was it? Yeah, locals. Yeah, we basically write, yeah, we got the local, because we don't really care about the types too much. Okay, we're just gonna write the ID and the local expression. Oh, hang on, getting that returns an expression. Yeah, that makes sense. So this really prints the ID and then the expression. Yeah. Okay. Yeah, I'm not too sure about indentation and how we handle that, but I guess we'll figure that out as we go. Yeah, parameters don't exist. Yeah, we'll do something very similar to this, except that we will just print the expressions, I think. Switch on the kind, and this is basically, yeah, let's remove that and replace that with this part right here. Okay, so parameters cannot be contained in bodies. They're only used as function parameters and they're not explicitly printed in here. Then padding, we'll just write padding, I guess. Oh yeah, it should also have the amount. Yeah, byte. Or just write the byte. Maybe then colon byte to indicate that this is a byte. And similarly the word would write that same thing with word. The local can write the ID. Oh, struct is interesting because a struct in here doesn't really have, you know, field names anymore. A struct just refers to some memory that lives next to each other, like an aggregate memory part. Yeah, let me maybe write it like this. So we have braces, and inside of them we have the struct expressions. Yeah. Oh, so writer dot like for field, I guess, and struct point the field. And also there should be comma separated, so first and then first is false, else. And we also print a comma in there. Yeah, members are interesting. Basically, members should be they should just have an offset, I think. Oh, and they have an off thing. Like, of what expression do we want the member? waffle member of something else. Yeah, and this is used for accessing parts of some other value. For example, in struct, when we access foo.y, really we create this expression that just has memory containing the fields, and then we say dot member 8 because the y is memory layouted in here at an offset of 8 bytes. Yeah. Similarly here we switch on a bool, and the bool is just a 1 byte tag. Yeah, so we have this struct thing, and we do dot member, so it's not really needed, I think, in this case. But for example, if you would switch on this part right here, on a maybe, then you could use dot member 8 to extract basically only a reference to this last byte, and then switch on that. So switches always work on bytes in this case. We don't have explicit enums anymore, we don't have any of that, it's just memory and bytes. Okay, so a switch. I think we basically want to print what we switch on first, like switch dot on, I don't know, condition maybe, byte, makes sense. Yeah, then percent thing, and then for each case in the switch cases, yeah, which are waffle bodies, sure, we print a backslash n and then the case. Hang on, now we want to do that indented, so we do write something like the body function. What was that here? Yeah, we want to call this function body fun and indentation. Body fun and indentation +1 in our case. Yeah. Oh yeah, this should also print the index of the case, which is basically like the key. So yeah, this is not actually like, we need a case dot item down here, and we have the case dot index, which is the actual like index. I feel like I'm not explaining this very well, but okay, then calls. Waffle call. I think we don't have a call in here. Okay, yeah, I guess I'm just going to print space separated things, maybe with parentheses around them to make sure that it's not ambiguous. And a call has a function and arguments. Okay, we can do this. Yeah, basically I want to write this. The function and then the arguments. Oh yeah, when we call ourselves recursively, we also need to pass in the function and the indentation. I think I haven't done that. Yeah, up here. So this also needs the function and indentation. Okay. Yeah, finally, for an instruction, it will be very, very similar to this one because it's basically a call of some built-in thing. Okay, call.function.debug with the instruction. instruction dot instruction, I guess. Is that how it's called? Yeah, it is. Well, okay. Oh yeah, and the arguments are basically converted into a struct thingy, like into a single memory layout. We don't have a concept of multiple arguments here. So we don't actually need this. We can just write the args directly. Yeah. Okay. Let's maybe let's not compile the actual file. Yeah. So in here, to test things, I created bytecode manually. And now I want to create, you know, a waffle manually. So this would just be a waffle with functions, which will be a map from waffle signature, which just contains strings. So we have one function called a that maps to a waffle fun. Yeah, and maybe let's also add another function b that also maps to a waffle fun. Yeah, waffle fun has locals, which is just a list of waffle expressions. That's nice. So this will be a waffle expression. Well, what do we want to do? I think let's just write a function that just returns sum 5, because why not? Okay, so this will actually be an empty slice of waffle expression, and it returns a waffle expression of size 9, alignment 8. Yeah, basically this thingy, or like this thingy. And that's a struct. So kind is waffle expression kind.struct. Containing a slice of waffle expressions. Yeah. So in here we have a waffle expression, which will be the number, so something with size 8, alignment 8, and the kind is going to be waffle expression kind dot word of 5. And then we basically have the same thing for the tag, which will be a byte 1. Whew, okay. Nice. Yeah, we basically have a function called a that returns sum 5. And now let's create a function b that calls that first function, and I don't know, switches on that maybe, and then either returns the 5, or it returns, either if it's sum, then it returns the contained value, or otherwise it contains 0. It returns 0, yeah. So let's first call the first function. So this will be a waffle expression. I don't know the size and alignment yet, but it's going to be a call. A call of some function with arguments. Okay, so this is waffle. So we call a arguments, and yeah, function call arguments are always laid out in the struct, I think. So let's just say this is a waffle expression dot waffle expression, where the kind is waffle expression kind dot struct, and it is empty. Yeah, empty slice of waffle expression. Beautiful. Of course, this has a size of 0 and the default alignment of 1. And calling this returns this. It returns the sum, so it has the same size and alignment. Okay. Yeah, that is our local variable. Next, what does this function return? Well, it returns a waffle. Oh, it returns a switch, basically. A switch that results in a number, so something that of the size 8. Oh, hang on. Hang on, this makes more sense. Yeah. An int, which means this, and it's going to be a switch containing a waffle switch, containing a byte and cases. A waffle switch containing a byte and cases. Okay, yeah, cases is basically a list of waffle bodies. Yeah, we don't call anything. Oh man. Okay, so it switches on, well, the tag of that previous thing. So basically we get we want to do something like this. So we need a member waffle expression. Yeah, this is going to be a byte, so size 1, alignment 1, and it's the waffle expression kind dot member. Yeah, member is waffle member of something at the offset 8, and that something is a waffle expression with size 9, alignment 8, kind waffle expression kind dot local. Containing a local ID, which is just an index into the locals thing. So that contains a local ID with index 0. Okay, so we basically take this waffle expression and then we access the member at offset 8, giving us the tag of the enum. And then we switch on that byte, on that tag, and the cases that we get from that, like the cases that we handle, there were 2 cases. The first one is just going to, that's the none variant, I think. It's gonna return 0, so locals will just be an empty slice. And returns is gonna be waffle expression of a number. Waffle expr kind dot int, yeah, returns 0. Beautiful. Okay, and the other case, yeah, it's also going to return a waffle expression with size 8, alignment 8, but a different kind. Namely the kind, accessing the payload of the struct. So this would be a member of that. Of that result of the call. Yeah, let's maybe copy the member thingy. Of this waffle expression at offset 0. Yeah. Okay. This is quite complicated. Quite complicated. Indeed, this is a waffle call with a function and the arguments are not expected a closing brace. I don't quite get that, to be honest. Oh, hang on, is there like a recursive thing going on? Probably. Yeah, there is. Okay, so yeah, the Martinez compiler doesn't handle recursive types well right now. Like it should just print an error, but yeah, this is a slice, that's fine. This should contain a pointer to a waffle expression, similar to a switch, and to the calls. Yeah, something like this should be better. I don't care about quick fixes. Hang on, let me maybe no. Restore my editor tooling. Okay. Okay. Okay, it should print some errors in here. It doesn't. I don't know why. So let's maybe compile that. Yeah, that's kind of what I expected. Okay. Yeah, this should be the lower byte. And then up here, the waffle fun must return a body. Oh, hang on. Waffle fun. Locals and body. But hang on. Oh, I see. I see. So this is a slice of the actual expressions, and the waffle body locals only contains an index into that. Sure. Yeah. So basically this is going to be a body that then also returns, or has locals, being an empty slice of that, and then the body contains the return value. Yeah, okay. Try to assign Waffle's signature. Oh yeah, that makes sense. This put on heap. Put on heap. Waffle member of this thing put on heap. Meh. Oh yeah, this is dot word. True. Yeah, this should be Waffle with local IDs, I think. Yeah. Okay. Pretty cool. Pretty cool. We're working our way up, basically. Yeah, indeed. Oh yeah, so here the body actually has locals, which is just a list of IDs that should be evaluated before the returns thing is evaluated. Yeah, so locals, really, they are just yeah, local ID 0, which means that first we call, like actually execute that, we call that other function. Yeah, and then we return this expression, which can depend on that. Expected closing brace of the block. Oh, I see. Makes sense. Oh, it's a list. Well, it's supposed to be a slice. Sure, we can do that. No more errors. Well, okay. In the yogurt we had some, yeah, we basically had some helper functions which were also needed to be able to use things as keys in a hash map. So I think we need to add those for the waffle as well. Also, like, local ID is pretty, like, it's not prefixed. Let's instead call this waffle ID. And then in here as well. Yeah, no, let's comment that out for now. You may need that, but oh yeah, this is called string. Makes sense. Yeah, up here we have this. What? Okay, so apparently it runs. That's pretty cool. So we should be able to print this, right? Oh, okay, they will probably do lots of different errors. Yeah, okay. Ah, yeah, so printing waffle ID is something that we don't do yet. But we should be able to do that. Similar to this. We'll just write the entire expression, and that includes like the access of the kind happens down here. But it still doesn't work. Okay, so why doesn't it? Call waffle expression, waffle fun and int. Waffle expression, waffle fun and int. Okay, what now? Oh yeah, printing. Why does that happen? Waffle expression. Then we'll just print the waffle expression. Let's see. Here we print them with, like, explicitly with a write function. Oh yeah, here for example. Really, we should call write the byte expression using the fun and our current indentation. Yeah, the indentation that we need to. We don't ever print indentation right now. Same thing later on. Okay. This works. This works. Here we do that as well. Then in here. Huh, okay, I don't know where that happens though. Print waffle expression. Int. I don't know why. Please show me. I don't know what to do here. I guess. Oh yeah, here. This is so small. You can easily overlook this. Yeah, but this is not correct. We want to print member of with the fun and the indentation, and then that. Beautiful. Oh yeah, and we need to dereference that here as well, probably. Yeah. And down here, not because that's just nice, but here and here as well. Okay. Body.returns. Well, indeed. Indeed, we want to print body returns, but with the local function and indentation. Oh, what? Okay, so we can kind of print things. Oh, I see. So this is function A, which just returns that 9 bytes of memory. So the first 8 bytes, first word containing the number 5, and then 1 byte containing the tag 1 to indicate this is, like, this corresponds to the value sum 5. Okay, and then function B should call that expression. Yeah, 0 equals that. Oh yeah. I mean, hang on, we should be able to just not do this. Okay, yeah, so this calls A with an empty, with no arguments, basically. Beautiful. And then it switches on that. And if it's 0, then it results in just the number 0, otherwise in the payload of that enum. That's pretty great. Okay, so yeah, fixing the annotation is probably the first thing to do. So, yeah, first of all, when writing functions, I think we want to put a new line after that up here. And also, let's say that each, I don't know, expression, each line is responsible of printing leading annotation. So this is perfect, I think. This is also perfect. The switch is not perfect, but just because, yeah, and here, basically between these, we need to print annotation. Otherwise, oh yeah, we should print a new line here and annotation, but like that. Yeah. Okay. This looks fine. Function A returns a value. Function B calls that, switches on that. Oh yeah, hang on, these should be indented one more. And this should actually be +2. And then here we have that. Yeah, I think, yeah, that's a bit better. 0.member8, switch on that, boom. Okay. You know, converting this to bytecode seems a lot more reasonable than converting the yogurt that we had before, because this is already quite, you know, we know the memory, we just deal with memory stuff. Okay, yeah. So we have the waffle stage. We don't like compile to the waffle stage, and we don't compile the waffle stage to something else, but at least the stage itself exists. I think the VM defines the bytecode instructions and all that stuff. Yeah. Right now, basically we have the definition of a compiler stage, and and then afterwards the code for converting to that compiler stage. So for example, when parsing something, we first have the definition of like what kind of things do we want to have in the tree, and then sure, we have some functions for writing that, but afterwards we have the entire like parsing stuff. Yeah, I don't want to do that here because I like that this file is basically self-contained. It doesn't depend on the compiler really. It just has bytecode and can execute that. Yeah, it's kind of weird that the like universe is a weird name for this file, first of all. And second of all, well, yeah, I'm gonna refactor this. So, like, I think I'm gonna split this file up into one file that converts Waffle to this bytecode. And in the Waffle file, I will add the code for converting yogurt to Waffle. So I'm just gonna create Waffle to bytecode. Yeah, kind of weird and inconsistent with how the rest is organized, but well. Okay. You know what? Let me maybe import that instead of the universe thing. So Waffle to bytecode. Great. Yeah, expected definition. What's going on here? Doesn't make any sense. I'm just gonna add it to bytecode function. Takes a Waffle, returns, I don't even know. What was that in here? Oh, returns an address. Right, an address of some place that contains memory instruction things. Okay, so let's maybe copy all of that, and then this is so weird. Why is that? Does the same error happen here? No. Maybe do this. Okay. Yeah, we reserve memory. We should reserve more, I think. Or like be able to grow with that, but well. Okay, so we have a map from Waffle signature to address. We have patches when we want to call other functions. Yeah, and then for each function, we get the function, save its address, and then we actually compile the function. Yeah. And then we fix the calls, and then we get the main function of int, which, yeah, I don't know how. Let's just put the main int in there. Yeah, this is gonna be the string, right? Something like this. And yeah, this should should look pretty much the same. Yeah, except let's call this Waffle. Cool. We have bytecode builder. We lay out parameters on the stack. Oh, hang on. Do the functions have the functions have IDs, okay. But then down here we just have a single waffle expression. That's kind of strange, to be honest. I think it totally makes sense in here. Well, let's go back to do. Does this make sense, or should we pass the struct like arg thing? Yeah, we don't have any, like, there is no concept of capturing things or something like that in the Waffle. Look, like all of these to-dos that deal with closures and stuff, like we don't even have memory layouts. Hang on, like what is this? You know, we have a Waffle. We don't need memory layouts here. No. Nope. 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 Yeah, we do somehow have to do this. I don't know how, but there's a to do there. So okay, bytecode builder has instructions, sure. Stack mapping for the local variables, makes sense. Then stack size is an int. Then we have add mapping. Okay, makes sense. Find a distance from top. Let's call it like absolute offset or something, just to make sure that this is not like relative to the stack top, but this is inside of the stack model. Yeah. Okay. Yeah, that makes sense. We can emit a bytecode instruction. Sure. We can check what's the, like, how those instructions affect the stack size. Oh yeah, this is not something that will like no, okay. I'm gonna leave it here. Sure. Then copy from stack. Yeah, copy from stack again. Sure. Or with a Waffle ID. Then with push value, which doesn't need to exist anymore. That's already a huge relief, I think. Yeah. So fun compile. Compiling a Waffle body means that we go over the expressions. Now, first we go over the locals, and we build those, and then the return value. So I think we'll have a separate, a separate function for compiling, for basically doing this. So we have compile an expression using the builder. This is the current function. This is the entire waffle thing, I'm sure. A list of patches. Yeah. We do nothing about like layouting or something. But we know that expressions have an alignment. And we add a mapping. No, not really, because we don't have an ID. Hang on. I think in here we need to do that in here, yeah. So we align the stack to the alignment that the expression requires. We add a mapping, and then we call compile on the expression. The expression.compile using the builder, the fun, the waffle, and yeah, the patches. I think it makes sense to move the patches into the builder, but I guess later. Okay, yeah, local is not a field on waffle body. Locals, true. Yeah, something like that. And then type is not a field on waffle expression because that is true and we don't need that. Beautiful. And then we look at the function return thingy, which will be, hang on, body.returns, yeah, just body.returns, add a mapping of the local, nope, of, yeah, we don't have any mapping for that, makes sense. And we compile what the function returns. Yeah, we don't have any parameters for bodies. Beautiful. We should have some compile function thing that does this. So maybe let's say compile waffle fun. Yeah, we need to basically call this other function, but then for body we don't need to, we just compile the body expressions. First the local things and then these ones right here. Oh yeah, and at the body, oh right, at the end we also need to, okay, we do somehow need to do kind of this. Not really, but again, this is not, first I want to get into compiling expressions. So compiles a waffle expression. Compiles an expression. assumes that the stack is already aligned for the yeah, let's move the patches into the builder. Bytecode builder somewhere up here, right? Yeah, bytecode builder patches. I'm gonna move them in there. Yeah, which means we need patches up here. Oh, here's the waffle fun. Oh, I see. Here we get past the patches explicitly. On the bytecode builder is explicit, like is created for each function. Sure. Yeah. We're gonna figure that out later. Yeah, that doesn't exist right now. Maybe go from the bottom, kind of, like, I'm just gonna comment that out, and then switch, and then see where it complains. Okay. I mean, yeah, I can also just copy these. And types don't exist here. Oh, come on. Okay, so param is unreachable. Yeah, if we just want some padding, we're just gonna do builder dot, what was it, emit push padding or something? Push padding of that amount. Okay, creating byte would just mean builder dot push byte, or builder dot, rather, yeah, builder emit something to push that byte. Yeah, bytecode instruction dot push 8. Of that byte. And I can see that basically instead of intermingling this code of converting things to a stack-based bytecode and dealing with memory layouts and so on, instead it gets simplified so that the complexity of the memory layout is contained somewhere else, and here we just push bytes. Yeah, for words it will look pretty similar. Basically pushing the word. For a local thing, we will do this copy from, yeah, builder.copy from stack. The local and the size. Ooh, I guess we kind of need that. Yeah. Yeah, for struct. Now, this is cool. We will just push. Wait, we don't have a memory layout. Or this. Or this. And padding is explicit, so we just do something like this. We just iterate over the fields. And we compile that, basically. And that's simple. For a member, so we know that basically a struct is on the stack, and we want a specific member of that. So we need to figure out, like, we have the offset. Right, first member.off, member.off.compile. Yeah, this doesn't make sense. Builder find waffle. I think we can simplify that further later on. But okay, so first we compile the thing that we want to get the member of, which means that is on the stack. And then we want to basically get the specific slice of that memory that we are interested in. And we have the offset. And yeah, we can basically just pop the first part, I think. Like first pop the remaining part. Yeah. Okay, so the amount before the member inside of this struct is just the offset. The amount after the member is basically the size of the original thing minus the size of ourselves, like the target thingy, minus the amount, minus the member offset. Yeah. So we just want to builder.emit bytecode instruction dot pop the amount after the member. And then we want to emit top below top, and we want to skip well, our size. Yeah, I think this makes sense. Okay. Oh, switch is interesting. I'm gonna do that later on, because that's basically the only control flow that we have, and it's gonna be a lot more complicated. Then calls, how do they, yeah, look at this, like, that's a lot of code. Oh, okay, it's actually not as much as I feared. Yeah, for a call we have we don't have argument layouts and stuff, like the argument's just a single struct. And what we do here is that, well, builder.align to 8, copy them from further back on the stack to here. We need to, yeah, no, we don't do that as well. We just emit a call, right? I think so. Yeah. Simple. Yeah, we emit a call instruction. Of nothing right now. And then we add a patch, which the patches are now on the builder. And then oh yeah, we know the current instruction index. Yeah. Okay, yeah. And we want to put the receiver in there, sure. And then builder.stack size is that. Does that make sense? Return type of memory level, no. We have nothing like this. We only know a function returns something with a size. Yeah, I think functions should also have a size and alignment, right? Like of the return value, you know. Oh no, we can just say body dot returns dot size. Yeah. Body dot returns dot size. Yeah, and instructions are interesting. They are all different. So I'm just going to copy that from down here. Okay, yeah. Right. I think it makes sense to split this into a bytecode builder and a fun bytecode builder. The fun one maintaining the stack and also having a reference to the currently compiled function, and the waffle. Yeah, then we only need to pass around that fun bytecode builder. Or let's do that. Yeah. So we basically want a bytecode builder that just has instructions and patches. Then the fun bytecode builder, yeah, basically has a parent, like a bytecode builder, and it has stack mapping, stack size. It has also references to the current function and to the waffle. Yep, makes sense. Okay, so then we have add mapping, which takes I mean, this is only called for locals, right? So tend towards not actually. Yeah, not actually providing that, but just doing that directly. Well, but then again, this is fine. This is totally fine. Okay, yeah. I think instead of emit, we could have different, like basically a function for every operation. And then for things like call, yeah, we could also basically request the or like look up the function and add things to the mapping and patches and so on. Actually, I think that makes sense. Yeah. Would probably be a bit boilerplatey, I guess, but I think that's cleaner. Yeah. Okay, so we have image push 8 on the fun bytecode builder and takes an byte. And it just does builder.instructions dot push bytecode instruction dot push 8 of that byte. Okay. A builder parent dot beautiful. And it does builder.stack size is builder.stack size plus 1. Yeah. And then we basically do this for every instruction. So push 64 takes word and adds 8 to the stack. Push 8 from stack. Yeah, this is an interesting one, for example, because push 8 from stack. Oh yeah, okay, takes an offset. Increases the thing by 1. Then we have push 64 from stack, increases that by 8. Then we have push below top. Takes the amount to skip in it and an amount, and yeah, here it has a tuple of the skip part and the amount. Oh yeah, pop. Okay, pop below top, we have that. Oh yeah, stack size is basically stack size minus the amount. Beautiful. Yeah, so jump is difficult, really difficult. Yeah, I mean, in those cases the stack has to be manually, like we need to manually care about the stack size anyway. So maybe it isn't a good idea to do this boilerplatey thing. Yeah, maybe not. Maybe not. Okay. Okay. so we have that. Yeah, bytecode builder, try to initialize field stack size, but bytecode builder doesn't have that. Indeed it doesn't. It doesn't. Oh, hang on. I'm back. So, yeah, where were we? I mean, I guess I'm just going to go through this file from top to bottom and figure stuff out. Okay, yeah, this seems to make sense. Let's give us a little bit more leeway, you know. Okay, and then signature to address. No. Is map. We have patches, makes sense. Yeah, and then we have the functions. They have the signature and the key. In here we put the signature. Okay, and then we compile the function. Yeah, when compiling the function we don't even need the signature, I think. Nope. And I think this should be packaged up in the bytecode builder. You could also like put the waffle in here directly. Yeah. And maybe instead of having the parent here, let's just copy these down. Because yeah, why not? It's a bit cleaner, you know, so we don't have to always go through the parent indirection. Yeah. Which means that up here we don't, like this just accepts bytecode builder, like let's say builder, just bytecode builder. Fair enough. And then it creates this builder, which will be a fun bytecode builder, and where instructions are, well, the instructions from the builder. And the patches are the patches from the builder. And what else does it have? It has instructions, patches, stack mapping, stack size. Yeah, stack mapping and stack size. Stack mapping, stack size. It has the function, and it has the waffle, which is a builder.waffle. Yeah, let's maybe organize this over there, so then, yeah, I think that's fine. Okay, very cool. So we want to lay out the parameters on the stack. Yeah, I think this is just, oh, yeah, we need to do this. And when, yeah, and then we compile the function body, builder.end of fun, and body.compile. And that calls something down there. Yeah, you know, let me move this entire thing down as well. So we first have the bytecode builder as like a helper class with all its glorious things. And then down here we have the actual compilation. Cool. Yeah, I'm just realizing we have two functions for compiling a function. That doesn't make much sense. This makes sense, and laying out parameters also sounds reasonable. It's probably not gonna be anything with memory layouts and params and so on. Yeah, the entire function is one body, so what remains on the stack after the body compiles will just be the you know, the return value. We don't have any locals that we need to pop. So we don't need to push this or pop these locals. Though we do need to do that in the body. Do we have the code for that somewhere here? Not really. Okay, so, oh, hang on. Down here? Nope. Okay, so I am going to copy this code. Basically down here and adjust that later. Okay. So we make space for parameters, we compile the body, which should just take the builder. Oh, and that's it, actually. Crazy. And then we should not need to do this. This kind of makes sense. Well, yeah, we should not need to do this, but instead we just emit a return instruction. Nice. Again, I'm gonna put that somewhere here. Okay, compiling a function. What's this? This does not work because this is supposed to accept a fun bytecode builder, so it doesn't need a fun or waffle or patches. Instead, it just compiles a function body. Yeah, this can be simplified as well. This just needs the builder. Yeah, so we should create a builder. Builder is bytecode builder, and instructions is a pointer to our instructions. Same with patches. And then in here we only need a pointer to the builder. And that's maybe inline function value in the key. Put function key versions.data. Don't get ref to address. Okay, yeah. Address of the next instruction is that. Okay. Waffle field is missing. True. Gotta add that. Okay. Yeah, this looks reasonably reasonable, I think. You know, we create instructions, signature mapping, and patches, create a builder, and then we compile every function. They just add instructions to the instructions list, they add patches to this, and yeah, in the end, signature to address is filled. We fix all the patches. Do that here. Yeah. And then finally we return the address of the main function. Great. For a function builder, we also create a builder first. That includes the stack model, and then we make space for parameters, which we still need to figure out. Sure. We compile compile the body and we emit a return instruction, because the body only leaves the return value on the stack. Yeah. Oh, hang on. To do push pop parameters, because the parameters are still there. Because the body, they are not locals of the body. Okay, then compiling a body. Means we compile the locals. Okay, we get the expression. We align the builder. Fair. Yeah, I think these should all just be in the fun bytecode builder. Padding byte is not in scope. I see. Builder.parent. Parent is not a field on fun bytecode builder. Yeah, true. That's just instructions. Okay. Apparently padding byte also doesn't exist. Hang on. I think it also actually makes sense to have a separate padding instruction. Like push padding. Yeah. Because later on we can just move the stack pointer and we don't care about the values that are saved there, you know. Yeah, which does mean that this is kind of useless. Because this could just as easily be builder.emit bytecode instruction dot padding, like push padding of that. Great. And then down here fun is not in scope, that's probably builder.fun. But also not really, because this should just take the builder. And here as well. Yeah, params is something that needs to be done up there. And here we just check the size of the locals, which will be the stack size. Let's do that here. Nice. Then we build the return value. Return value size is yeah, we can just do body.returns.size. And then we pop the locals. This call doesn't work, okay. Why not? We compile. Yeah, compiling an expression should just take the fun bytecode builder and that's it. this will be init bytecode instruction dot push padding with an amount. Beautiful. Yeah, this can just pass the builder in here, and yeah, similar here. And pop right. Pops the amount. Simple. And this is so elegant, honestly. And the local as well. Dang. Crazy. Yeah, here we have. Yeah, let's do this last. You know, first the call. We made a placeholder call, and for the patches we push I've seen this before in, well, kind of something like that. Somewhere for the locals, I think. Not really. So the address of the current instruction. Oh yeah, this right here. Yeah, I think I'm gonna add a helper function for that. There's something that address of next, something like that, of a slice of bytecode instructions. Oh, hang on. A list of bytecode instructions. And this just returns an address because it returns instructions to data, which is a slice, dot get ref of that converted to an address. Yeah. And yeah, this can just be, yeah, this is pretty descriptive actually. Yeah. Maybe ref of next. Bytecode instruction. Yeah, something like this. And then in here we can just say address of the next instruction. Instructions dot ref of next dot to address, and it's actually inline, right? Yeah. Beautiful. And down here we can then say call ref is builder instructions dot ref of next. Beautiful. And then here we can say we have a new patch. Please patch this function. Yeah, hang on, when calling something we also need to like build the call.args dot so the arguments are on the stack. Yeah, the argument should be on the stack. Then we emit a call instruction. Yeah, and then the stack size is adjusted by taking the current stack size. Yeah, the arguments are now consumed, and instead the function returns. I mean, that's just expression dot size. Nice. Yeah, instruction.args is just a single thing. So we do instruction.args.compile using the builder. No memory layouting necessary. Beautiful. Okay, yeah, and this doesn't happen on every expression, only after a body is finished. Okay, yeah, so much simpler. I mean, look at this. Most of these are just single, emit something. For struct, it's just compile all the fields and that's it. Like, the complexity of this code is much more reasonable than what we had previously. Okay, switch is going to be a bit like the trickiest one, because that's actually control flow. So let's implement that. We have instructions. Okay, so we do push from stack of the condition. No, not quite. We just say switch.byte compile using builder. Yeah. Here we can say builder instructions ref of next. And then we say builder.emit, bytecode instruction dot jump table. Seems correct. Yeah. Oh yeah, but it needs a slice of addresses. Yeah, I see. So this will just be an empty slice. And then we say table will be a list of addresses. We have a list of end jumps, which will be bytecode instructions that need to be updated. And then for every case in the switch cases. Oh, this is so nice. We know the case index. Oh, no, we don't even need to know that, because we can push that. And we push builder.instructions.ref of next. So we know that the next instruction that we have here will be that. Yeah, let's let's maybe convert that to an address. Okay, that is beautiful. Yeah, and then here we do stack length things and so on. Yeah, no, we don't need to do that. We just compile the body. Case dot compile like that. What? Yeah, then we have parameters. Nope, we don't need that. Yeah, here we compile the body. Oh, look at that! All these arguments. No. Pop things, we ignore things. Not really. I don't even know what's going on here. No, we don't. No. Yeah. Okay, so emit jump table. Jump table. Yeah. Like these need to be manually adjusted. I think. Yeah, basically when we have a jump table, we have to say builder dot stack size. Could say -1. Yeah, because after the jump table instruction, it consumes 1 byte and jumps somewhere. And then here we have size at case stack size case, something like that. Yeah, we build a table. Say end jumps. For each case, we basically say, well, yeah, table dot push that. Yeah. Then we say builder dot stack size equals stack size at start. At start of case. We compile case. We push builder instructions next. That is a jump that we emit here that we need to update later on. But it needs an address. Sure. And then we have the end, which is just builder instructions dot ref of next to address. Yeah. Oh, look at that. That is beautiful. You just fix the jumps like that. Yeah, we can turn this into jump table. Damn. That is clean. And it's a slice. I mean, this fits on one page here, on one screen. That's pretty amazing. pretty amazing. Okay, yeah. Align to doesn't work, okay. Oh, waffle expression, no, returns dot alignment. What's going on now? Body is not in scope, yeah, okay. So, a function has parameters which somehow exist. Does it though? I mean, yeah. I think in the waffle, okay, so a function doesn't have any parameters. Should it have some? I think a function should know, it should kind of know what the size and alignment of the parameters will be. You know? Oh, wait. Now we could just say function parameters are modeled as, you know, the body containing a waffle ID. Waffle ID, yeah, that makes sense. Parameters. Functions here don't explicitly contain parameters. Instead, the local represents the parameters. Yeah, that makes sense. That makes sense. Yeah. And that means that it is guaranteed to be on, is guaranteed to exist and be on the stack when the function starts executing. Beautiful. Okay, yeah, so actually let's take the fun dot locals get 0, which is guaranteed to exist. And slice waffle expression. Yeah, now we have a waffle expression. Now we wanna, you know, align our stack and add a mapping and stuff like that. And most importantly, compile that. Yeah, kind of like this. So we have params from locals get will align to params.alignment, which, I mean, it's aligned to anything actually. So we can just add a mapping. Waffle ID, yeah. I think this needs let's do it like this. Waffle ID with index 0. Then here we can say it's that, and this is params. Yeah, that makes sense. Yeah, builder should probably be mutable. And here we compile a waffle expression using a mutable builder. Yeah, and that also adjusts the stack parts. Yeah, okay. Beautiful. Yeah, size of params. Yeah, we do kind of need to yeah. So we compile the body. Now and it contains the params and the value should be and the return value. So we basically emit a bytecode instruction dot pop below top, where we skip fun.body.returns.size, and we pop fun.locals get zil.size. True. Oh, hang on. No. This is guaranteed to be a params expression, right? Yeah, and we shouldn't compile that. True. Yeah, so that's instead we need to adjust the stack size manually. Yeah, we can say params ID is at 0 and the stack size is params.size. That's the initial stack. Basically, when we start the stack against the params. Oh, we don't need this. Yeah, this is cool. Yeah, stack containing the params. So now the stack contains the params. Now the stack contains the params and the return value. Now the stack contains the return value. Damn, that is clean. Super clean. Yeah. You know what? I'm going to take the reference directly here. Because for builders, we always need mutable builders anyway, so. This is just beautiful code. Okay, what's going on up here? Funds field is missing. Get Waffle, or Waffle ID, right? Or Waffle signature. Yeah. Then up here we don't handle push padding, indeed. Here's push padding amount is just amount. Dot handle pop. Yeah. I don't handle, yeah, I do. Okay. Wow. If you add enough like helper builders and so on, your actual code is pretty cool. Like, this is nice. And this also clean. Oh yeah, we need to do this. Yeah, size of locals, and we have the return value size. Now we basically want to do builder.init bytecode instruction dot pop below top of the ones we want to skip, which is the return value size, and then the this stack size is body start. Let's call it locals size, so it's consistently named with return value size. Yeah, and then we pop the locals, and then we return. No, we don't return. Not that. We just end with the return value on the stack. Yeah. Beautiful. Okay, then compiles an expression. Assumes that the stack is already aligned for the expression. Nice. Again, this is so nice. And even this is quite readable. You know, the fact that we store these basically references to the instructions, and then we can just update them like this. That's beautiful, and so much cleaner than storing indices here. Nice. Okay, yeah, I really like that. Yeah, I guess next. Oh yeah, I want to make it a bit more, you know, a bit more readable, I think. Like, basically create helper functions for creating Waffle stuff. Yeah, so in the plum, we create a Waffle manually. And a lot of these size and alignment things, they can be calculated, because the size and alignment of some expression is just, you know, the sizes, for example, for a struct, it's the sizes of the children added, and the alignment is the maximum alignment of them. For a switch, it's something else. So I think it makes sense to just have helper functions for the expressions that will not just make the main function cleaner, but also when later on creating Waffle from yogurt, the code of that will get cleaner as well. So I want to be able to create Waffle padding with an amount, and that should return a Waffle expression, which will have the size of the amount and alignment of 1, and the kind will be, well, Waffle extra kind dot padding of the amount. getting a byte. Waffle byte of some byte. Then waffle word. That's size 8 and also alignment 8. Waffle ID, and that's kind of interesting. So waffle ID. Maybe that should take another expression. Maybe that should take an expression. No, not really. For now, let's just take the size and alignment. And yeah, results in waffle expression of that size and alignment, and the kind is waffle expression kind dot local of ID. It is local, yeah, let's call it local. And then there is struct. And this is just going to take fields, which will be a slice of waffle expressions. And the entire thing is going to return a waffle expression. Where, well, we need to calculate the size and the alignment. And I think the easiest way to do that is to just add up the sizes and get the maximum alignment. Nice. That's a struct. Then member. That will take some other expression and I think an offset and a size actually. Also an alignment, I think. Yeah. Interesting. Yeah, there is quite a bit of boilerplate. Off and what else? Offset, right. Oh, let's also do a sanity check. The offset shouldn't be like 100 if the size of the original expression is only less. So basically offset plus size should be less or equal than offset size. Yeah. pretty cool. Then switch. Switch dot off. No, hang on, switch on byte. And then we have the cases. Switch byte and cases, which will be a slice of waffle expressions. Yeah, hold on, hang on. Okay. I think I want similar assertions. So for switch, okay, we need to figure out the alignment, which will be the maximum alignment of the fields, of the cases. So for each of the cases, basically say the alignment is the maximum of the case alignment, yeah. And then all of the cases should also have the same size. Yeah. So, and there should be at least one case. So case.length is not empty. Or we panic. You know, switch with cases. And then we have the alignment 1. Yeah. And yeah, let's maybe also do it like cases dot get 0 dot size. And then we ensure that the sizes also match. So size should be case dot size. Switch cases have different sizes. Nice. And yeah, in the end, we create a waffle expression similar to this one with the size and alignment, and this is a switch, which is a waffle switch with a byte and cases. It's super nice to have these, sanity checks in here. Nice. Yeah, call. Call. That's interesting. Yeah, waffle call. And it has a function. It has args. I'm just wondering, when we call a function, I think we take the maximum alignment of the return value and the arguments, right? Like, even if we have a function that accepts an int and it returns a byte, then waffle call will still be aligned to 8 bytes. Yeah, makes sense, I think. Yeah. Yeah, okay. In struct, yeah, that's also, in struct we also need to check the alignment of the fields. So if you have a struct and you try to create a waffle struct with a field of alignment 1 and size 1, and then a field of alignment 8 and size 8, that doesn't work. Because the previous fields need to have a multiple, that the size of the previous fields needs to be a multiple of the current alignments, something like that. So basically field size is multiple of, right? The existing size must be a multiple of that. Yeah, that doesn't exist, but we can do, let's see, the size is multiple of. Oh, let's add that. Standard lib int. It does have round up to multiple of, yeah. So I think it is fine to also have a check, which just checks that. Okay, yeah, actually. What's going on here? Interesting. I would have assumed that we could just do number divided by factor times factor is number, and we can probably do that. Yeah. Is multiple of factor. Yeah. Nice. Okay, yeah. Cool. So, byte is not in scope, true, because this is supposed to be a waffle call with a function and the args. Like that. Oh, yeah, these are waffle bodies. Sure. Yeah, waffle bodies don't have a size or alignment. Well, don't they? I mean, they could have. You're just saying, like, when running this body, yeah, they should have an alignment, I think. Size and alignment. Yeah, then that makes sense. body dot size should be the just the return values size basically. Yeah, and alignment should be the alignment of the cases. Yeah, okay. This looks fine. Okay, so we have a call next. Instruction. Yeah, so yeah, that is kind of right. Instructions are these. Something like concat strings should not be built in. Like, it shouldn't have a concept in the waffle where we just have, memory stuff, memory accesses and so on. So I think instructions are actually too high level to have in there. Yeah. Instead, let's instruction. Yeah, and this is waffle instruction call. I don't know. I guess. Yeah. This can already be the 64-bit numbers. Compare ints. No, it doesn't exist. No. Just that. Cool. Let's maybe. Okay. Yeah. Either we do this, or we just put them in there. That would also work. Yeah, I think I like that. Nope, not this. But basically inlining those here while giving them arguments. Because really the waffle is kind of like a higher level version of the bytecode in the end. Yeah. Yeah, and the arguments will basically be operands. I don't know. The Waffle int operands or something. Yeah, no. Let's turn these into just basically like a struct, you know. Yeah, that's better. That is much better. A struct that contains the arguments and that is, you know, specified, or like has a special, has a different layout per instruction. That's just guaranteed. Cool. So Waffle instruction, well, not really. Except that add 64. Yes. Which has left and right. Hell yeah. And it checks the left size is 8. Oh. Check. Int operands. Has int layout on an expression. Kind of like this. And this just results in a waffle, well, a waffle expression where the size is 8, the alignment is 8, the kind is add 64 of, oh, kind of like a waffle struct, I guess. So another waffle expression, 16, and the kind is waffle expression kind dot struct. containing a list of left and right converted to a slice. Yo, this is pretty amazing. Okay, yeah. And now I'm doing this for every expression. Well, waffle operands. Maybe int. Yeah. Oh, that is nice. I can even check this. There's no add and sub. And friends. Nice. This is pretty cool. Yeah. So this will not be, well, this will be that, but then we'll have waffle int operands of left and right. Beautiful. Well, I mean, in this case, I agree that beautiful is well, it depends on how you look at that. But still. Noise. Sub, we can multiply things, we can divide things, we can modulo things. We can end things, yeah, and or XOR, and we can crash things. And or XOR crash. Okay, and or crash, and here that doesn't make sense semantically in operands. So instead I'm going to create, it has pointer layout, I guess. No, it has word layout. Why not? Yeah, the end operands are that, and then the crash operands. We can do something similar. Yeah, crash with message pointer and message len. And we'll do something very similar to this, where we basically check very cool. This is just going to be crash, not crash 64. And this is not going to be that, but instead we'll just inline that, I guess. Oh, hang on. We can use our newly created Waffle struct thing, of course, to directly convert that list into a nice crash thing. Yeah, we do need to put that on the heap still, but cool anyways. Yeah, this is just waffle struct containing that. Nice. We could just check this word, because that's, you know, cool. Very cool. So now let's try to rewrite this into something a bit more concise. So this right here could just be waffle word, I guess. Waffle word 5. And the next one is just waffle byte 1. Like that. And then this right here is just a waffle struct of that list. Oh yes. And then the body has a size of 9 and an alignment of 8. I think we also need something for creating waffle body. Waffle body of locals, which is waffle ID. Let's create a waffle builder. Just has, I don't know, locals, which will be a list of waffle expressions. Yeah, and then you can say local a waffle builder, and that gives you something. That gives you a waffle ID. The idea is just going to be a waffle ID with the index being locals.len, and then it's going to do locals like builder locals push. The expression, and then it's going to return the ID. Great. And then there's a finish thing. That just returns a waffle. Oh, hang on. First, yeah, I guess a waffle fun builder is. Yeah, that returns you a waffle fun. That makes sense. Okay, and the waffle fun has or is it a waffle body builder? we also need a waffle body builder, which also just has, you know, a list of locals. Yeah. I think you actually do this on a waffle body builder. Oh yeah, and because a body also needs a size and alignment, I mean, the size is basically the size of the return value, but the alignment is important. Yeah, so on that body builder, you can define a local, which pushes that. But also, it increases the alignment potentially. So builder alignment is, you know, the maximum of the builder alignment and the expression alignment. Beautiful. Yeah, and then in the end you can say I don't know, returns on a body builder and with an expression that then returns your body. Which will be a waffle body containing locals, aka the builder locals, converted to a slice. It contains the return expression. Returns. That's just the expression. It returns the size. That's the return expression's size, and it contains an alignment, which is the builder alignment, which is the maximum alignment of the local variables. Okay, yeah, waffle expression for locals of ID. Oh right, because the body builder only has yeah, okay, that makes sense. So the builder has 2, and here it has the ID, which will be the local expos.len. Then it has local expos.push. It does, oh yeah, instead of returning an ID, that makes sense, it just adds the ID to this. So builder.local IDs dot push ID. Now let's invite that. Cool. And this will be local IDs to slice. Whew, yeah. And a waffle fun builder. By the way, you should be able to create those, so waffle fun builder. Creates a waffle fun builder with the locals being a list somewhere on the heap. And then you can call body builder, or like body on that, or like that, which will be a waffle body builder. Returns a waffle body builder, which will just be a waffle body builder with local expressions being an empty, being builder.locals. Local IDs being a list of waffle IDs. And alignment being 1 by default. Yeah, I guess local IDs is owned. So I'm just gonna do it like that. Probably makes sense. Yeah. It's even aligns, crazy. Oh. Oh. Okay, and then in the end you can say finish on the waffle. Oh yeah, we're gonna put that down here. On the waffle fun builder, returning the waffle fun, and you need to pass in a body. And that will create a waffle fun. Well, which has a locals list and a body. That's it. Locals with builder of local express and the body. Yeah. Oh yeah, locals. Crazy. Yeah, L is not a field on waffle fun builder. It only contains these fields. Locals. Yeah, hang on. Let's make this into that. No, we don't. But then this needs to be mutable so that we can take a reference to that. And then down here, we don't need to do that. Okay. Ooh. Okay, you should be able to call waffle fun builder. That returns your waffle fun builder. You can call body on that to give you a waffle body builder. Then you can call local with, several. It will basically define local variables on this thing. This could even return your waffle expression. Oh, hell yeah. Of the waffle ID, Ooh. Yeah. So basically you never need to do, this. Because this is kind of weird that you have to pass in the size and alignment explicitly. Let's remove this in favor of this. Yeah, local returns your waffle no, hang on, let's have both, just to be sure. That waffle local of some, no, where is it? ID, size, and alignment. Yeah, okay. So let's maybe use the ID in here. Cool. And then down here we have the locals. Try to assign this color to a slice. Sure, we can do that. let's see how this goes. Look at the indentation here. We can certainly improve on that. Okay, so waffle equals. We can create a fun. Oh, no, we can't. We don't have a waffle builder yet. Could create one. But I think this is fine. Yeah, so basically in here, we will do what? We will create a fun builder. That will be a waffle fun builder. And then we create a builder. That will be fun builder dot body. And then we won't create any locals, but we will say builder dot returns this, a struct with that, and that will return us a body that we can then use to finish the fun builder, like that. And I know here it kind of looks complicated, but we don't need to, calculate the size and alignment manually. Plus, plus we could theoretically also add local variables, which is something we're going to do down here. So fun builder is just waffle fun builder. In the end we say fun builder.finish with a body that we get from the builder returns something. And the builder is the fun builder dot body, and then in here we can say builder dot local waffle call of this signature with arguments being a struct, so being a waffle struct, without any empty stands without any arguments. Okay. And then we return this right here. And yeah, let's simplify that. So this is a waffle switch of a byte, which is a member of something of the local. So local returns some foo. We can say foo.waffle member offset 8 and a size. We also need that. Yeah, the size is 1. And that is basically this entire part. Crazy. Yeah, and then we have the cases, which will just be a list and convert it to a slice. Okay, and the first, so we have two bodies here. Now it gets interesting. So the first body is something, and the second body is also something. And here we create new builders. So we can say fun builder dot the body to get a new body builder. And then we can just say builder dot returns word 0 for the first one. And then later on for the second one, we don't have any locals, so we just immediately return. Well, what do we return? A member of the same local. So foo dot waffle member at offset 0, size 8. Yo. I mean, we can even do this because we don't need any locals. Just need a body that returns something. Damn. I mean, this is crazy, right? So much shorter. Yeah, we build a function, fun builder. We create a local variable, call that foo. We switch on the last byte of foo. I think waffle call also accepts size and alignment. And several things here don't quite work out. Oh yeah, that needs to be like that. And I think, yeah, this is supposed to be val. And hang on, yeah, I think the rest is actually fine. Yeah, exactly. This needs the size of the thing that it returns, which is 9 with an alignment of 8. Okay, local doesn't work because, oh yeah, it needs a mutable one. Okay, this is the signature. Oh yeah, also needs alignment, I guess. Yeah, size 1, alignment 1. And same here. Yeah, 0, size 8, alignment 8. Great. Well, waffle signature, waffle fun, and waffle signature nothing. Oh yeah. Indeed. Fun. Fun builder dot fun returns the body of finish with a body. think to make the structure more clear, I should actually do something like this. Body is this, and then in here we have the builder for the body. And yeah, kind of this, you know. Yes. And same here. Kind of only a body, which will be this. Noise. Yeah, and here we can also just simplify that. Like that. Cool. Yo. Let's actually look at the code, and we see that things don't quite work out. Because we have we need to print the waffle, and we've added several things, several instructions. So if it's add 64 with the operands, we're just gonna write, well, I guess add 64, and then the operands. I guess. Add some null divide mod and or XOR crash, something like that. Okay, so we've add mul, add sub mul divide mod and or x or not crash. Not just that. Sure. Cool. Very cool. Okay. So we can print, well, welcome to the Plum compiler. And then we have function A and function B. What is this? That doesn't look right. This calls A with 96. Call A with an empty waffle struct. That's what it should be. That's not good. What's going on here? What's going on here? So we have a waffle call. Correct. Of one argument also seems correct. Waffle call takes arguments. Oh yeah, no, we can't just do that. But we have to put it on the heap. Taking local references to things that are on the stack is they don't live long enough. Okay, so you have padding, local. Yeah, no, this also put on the heap, please. Yeah, same for calls. Yeah, this seems fine. Yeah, much better. Much better. We call A with an empty struct. Sure. That results in 0, local variable. We get the member at offset 8, aka this byte. And then we switch on that. If the byte is 0, then, well, we just return the word 0. If it's 1, then, well, we get the member at offset 0. Beautiful. And we can even, like, this catches some errors. If we return incompatible things. So for example, let's say this returns member 0, but it only has the size, like, size 4. Yeah. Switch cases have different sizes. That's crazy, right? That's super nice. Okay. Yep. I like that. Next would be converting that to bytecode. So waffle to bytecode. And I basically want to see this, you know, that returns bytecode. So this would be bytecode plus something. Oh, well, that is true. Push padding and pop. Need to handle those. Great. What's going on here? Oh yeah, we need to also actually do something. Well, yeah, I guess in here we can just, for now, push garbage bytes. Pop.
I mean, that is kind of equivalent to top below top, with top being 0, but yeah, I guess this is cleaner. You can implement it very... Oh, hang on. There is a pop with an amount of that. Yeah. Let's use that for padding. Where's that? Waffle to byte code. Here we need to... Oh yeah, basically inline these. Makes sense. We want to compile the arguments, right? Yeah, compare ins doesn't really exist, I think. And also the int suffix is just that. Yeah, this also doesn't exist, which is totally fine. And crash. Yeah, and instruction also doesn't exist because they are now all compiled inline in here. Yeah. Okay, I guess. Compile. Waffle fun. Oh yeah, we need locals. Oh, so I think the waffle fun builder. Where's that? Yeah. Oh yes, it needs to accept arguments, which will have a size and an alignment. Yeah, and this will be a list of a single waffle expression. Yeah, the waffle expression with size being args size and alignment being args alignment, and kind being waffle expression kind dot param. Yeah, so in here, yeah, the A function accepts something of size 0, alignment 1, and same here for B function. Ooh. Yeah, that's true. But this looks pretty cool. Pretty cool. Okay. Let's see. Yeah, so I guess this is the first function, function A. Yeah, we push padding 0, which, yeah, That's fine, I guess. Doesn't hurt. Yeah, then we basically push the struct. Just 5 and 1. And then we pop basically size 9. And those 0 below that, we pop them. Amazing. Yeah, in the other function, we push padding. Okay, then we call something. Oh, and we need to adjust the patches here. Push more padding 0, which does nothing. We push something from the stack. 1. Ah, yeah. That is the first, like that's basically the 5. And then afterwards we do push 8 from stack, that's the tag. Okay, pop 0 does nothing. We pop the 8 things that we got there, so that only the tag remains. And then we have a jump table. And the first case is basically pushing 7 bytes of padding. That is okay. And then pushing a I see. Yeah, because this is because we still have the tag on the no, hang on. Actually not sure. Okay, I think from the call we still have, you know, like 1 byte over something useful, so we push padding there, okay, I guess. And then we push 0, and then we push, yeah, we pop 8 below the top. Ah yeah, also popping the tag in the process, I think. And this is quite similar, except we push something that is on the stack. And then we push 8 from stack and pop that again. That's strange. Let's see. So I'm kind of confused. This call something. That is basically pushes 9 bytes on the stack. Right. Should do so, yeah. And then we push 0 padding before copying the struct there. That also doesn't seem right. Because in here, when we, this right here, basically should copy this, the result of that, on the stack, so that we can then discard most of that. I mean, yeah, that's inefficient, but still it should align this to 8 bytes. Should align that, okay. So I think I believe there should be something more here. I mean, I could print the size and alignment as well. So basically for each expression, after printing the actual expression, also print size and alignment. Okay, so we have 5, boom. We have 1, boom. Yeah, that results in this struct with size 9, alignment 8. Then we have this, yeah, basically calling A with this struct size 0, alignment 1, and that entire thing results in, well, size 9, alignment 8. Great. Then we refer to 1, which is size 9, alignment 8, and get member at offset 8, size 1, alignment 1. Yeah, that makes sense. That's the tag. And then we have 2 branches. First branch resulting in, oh, this is not correct. First branch resulting in size 8, alignment 8. Makes sense. Second one, taking this size 9, alignment 8, and getting the member 0. But then the entire switch should have an alignment of 8. I think the member expression here should also have alignment of 8. Because it gets the member of this thing, and to load that to the stack, it first needs an alignment of 8. So even when you want to lower this member thing, you actually need to push padding to the stack. Yeah. Okay, so let's see. Member, like fun, waffle. Maybe let's go through these and recheck the alignment. Okay, padding is alignment 1, byte, word. Okay, locals is created explicitly, and all of that works out perfectly. Then struct, the alignment is the maximum of the field alignments. Also makes sense. Member, yeah, I think the alignment should be the maximum of the alignment and the off alignment. Yeah. Okay, that makes sense. And then the switch. This is apparently where things go wrong, because here, when the alignment is the maximum of the alignment and the case alignment. Hang on, but oh yeah, let's maybe print that same suffix thing, this right here, after bodies as well. So we have the body, then the return value, and then the body size and alignment. Oh man. Okay, so member 8. Yeah, now this requires alignment 8. So that we ensure that we are at an alignment 8, so then we can do this. Okay, yeah, that makes sense. Then or does it? I'm gonna think about that later. I actually think the alignment should not. Yeah, because otherwise the alignment always bubbles up, you know. For example, if we create a struct and we want to create it with 3 bytes inside with a function that accepts ints with like very picky alignment. Then we still want to pack those final resulting bytes together. Yeah, okay. So alignment doesn't propagate upwards. It's just that if you have a child expression with a bigger alignment, then you need to add padding to the stack in an appropriate way, and then evaluate the child expression, and then before you evaluate yourself, basically, if you added alignment, if you added padding before, then you now need to remove that padding to shift your resulting value a bit to the backwards on the stack. Yeah, okay. Oh yeah, this is not correct. We have this word, and then the alignment of the entire body is 1. So, nope. Okay. Yeah, okay. I think the Waffle to byte. Yeah, okay. I think the body doesn't need alignment after all. Because this will just be the size and alignment of the return expression. Even if some locals have stricter alignment requirements, then those should be, the resulting padding should be removed before the body returns. Okay. Yeah, this is get 0, that's a body, and then say body.returns.size. And then down here, waffle body, field alignment, yeah, those don't exist. Just take the return thing and everything is fine. Everything is awesome. Alignment is not a field, that is true. We have the return alignment though. Waffle switch, hang on. Yeah, if they have different alignments, then the alignment should be raised. That, for switch, that's correct. Yeah, this, let's remove that. That's just the alignment of the last thing in there. Okay, let's double check this. 5 is a word. Okay, that looks correct. This as well. Then this entire struct has size 9, alignment 8. Beautiful. This calls A with this struct, correct. Results in this, correct. Then we take that with this alignment, correct. We have member 8, correct. That should be size 1, alignment 1. Yeah, so this should just be the alignment after all. Yeah, size 1, alignment 1. Okay, perfect. Then we have this, size 8, alignment 8. Or we have this, which is size 9, alignment 8, dot member or with size 8, alignment 8. So the entire switch evaluates to something of size 8, alignment 8. That looks correct. Great. Really great. Okay, this also looks correct. Pushing padding 0 and popping nothing, I mean, sure. Basically, we push the 5 and then the tag 1. Here we push some padding, 0, okay, fine. And then we call A. Yeah, that results in this. So now we have this on the stack. That seems correct. So So then we push padding, because now we want to copy that. And then we push the first part of that, like the 5. Yeah, and then the 8, which is at offset 15, that's correct. Nice. So now we have basically this on the stack twice. And yeah, popping 0, okay, sure. Popping. Popping below top, the tag, we keep that. But the first field, we discard that. Yeah. So now we have on the stack basically this from the call, then 7 bytes of padding, and then 1 tag. Let's see, pop below top, 1, 8. Yeah, then jump table. Amazing. And in the first case, we push padding 0, sure. We push 0, we pop the 8 below. Okay, that was the tag and the padding. And we jump to the end. Okay, in the other case, we do that. We push. Is that correct? Yeah, here we don't pop anything. That's okay. Yeah, we just result in the 0. Yeah. Push 64 from stack. Then we have 8. Oh, I see. Yeah. I think that's actually correct. Yeah. Yeah, we still have this struct on the stack. Followed by 7 bytes of padding. Followed by followed by now the original like 5. Yeah, and then the tag afterwards. We pop the tag and we pop 8 below. This is difficult to oh no, we don't pop anything. This is 0. Okay, so we still have, then this part basically, and then 7 bytes of padding, and then we have either a 0 from here, or we have the payload from here. And now, oh no, here we also need to pop the padding that we added. So this is not correct. This should be 16. Yeah, so let's see. Body, no, also, I think something like the same thing basically. We align ourselves to the locals. That makes sense, yeah. But then here, yeah, member. And then we say member.off.compile. We don't even care about padding here, do we? Where does the padding get added? I don't quite get that. Oh yeah, I mean this is basically like this. You need to align the builder, then we calculate the size of the locals, including the padding afterwards that the return value needs. Then we compile that, then we do that. Yeah. I'm gonna, hang on, push padding 0. At least, you know, when writing them, we can put them in parentheses or something. And same for pop below. And pop. Oh, hang on. Where are they? Oh. Well, no. Well, not here. I was thinking in the bytecode. VM. Yeah. Comment it out basically. Yeah, same for pop. And for pop below top. This is not clean or anything. Yeah. So the essential part is we push 5 and 1. We return, okay, first function. Second function, we call the first function. We push 7 bytes of padding. Then we duplicate that value. Okay. We pop the thing below the top. Okay, so now what remains is the... Oh, hang on, where does this padding get added? We have these. Align to, okay, yeah, the definition. And then before each local and return value. Okay, so that's how this gets there. Oh, and this is because the return value expects that amount of padding. now we have this. That looks correct. Yeah, okay. And here we basically duplicate that maybe. And then we only take the tag, we jump on that, which should automatically consume the tag. Yeah, and we just push 0, or we push those. And then this one, and then pop the 1. Yeah, okay. Yeah, that looks correct. Okay, although we should align things for individual expressions as well. So, okay, for padding we don't need to do anything. For bytes we don't need to do anything. For words, yeah, we can assume that the stack is aligned for this expression, but we may have children that are not properly aligned. That's the thing. Because for the struct we know that the children are, they will result in something, and then they will have, like, this will work. Because, for example, we don't allow a struct with 1 byte followed by a word. We need to have 1 byte and then padding and then word. Yeah. So assuming that the stack is aligned for our struct, we know that the stack should be aligned for all of our fields, based on how structs are created. But here's the interesting part. Remember, here we call member.off.compile, calling ourselves recursively, but here we need to make sure that we align our builder to that. So builder.align to, stack before is builder stack size, and then we align the builder to the alignment of our member.off.alignment. Yeah, then we can safely say, okay, please, call yourself. That should work. And then down here, we have the amount before the member that we want to pop, and the amount after the member we want pop. Let's do something like this, I guess. Stack before aligning and stack after aligning. Padding is stack after aligning minus stack before aligning. Sure. Then we compile that, and the amount before member that we want to pop is the padding amount. Yes, the padding plus the member offset. That makes sense. And the amount after the member is that, and then we have these two. Okay, that makes sense. Whew. Okay, yeah, switching, like the byte should have alignment 1, size 1, so this is not, hang on. Waffle switch. Yeah, let's check that. So byte dot size equals 1, or switch byte has invalid size. Same with alignment. Okay. Yeah, so we are always aligned for a single byte. nice. Then jump table. Hmm. We compile the byte. Yeah. Hang on. This is not correct. Because the jump table instruction removes the byte. Oh, hang on. Yeah, this emit also like decreases the stack size by 1. If, yeah, because jump table. Okay, yeah, makes sense. And switch. We have a switch and we wanna, yeah, for each of the cases we are properly aligned for the content. I think, yeah, that right here. Yeah, because the switch has the maximum alignment of its children. Okay, so this should work. Okay, great. Next, the call. And this is similar to what we have to do here. So we have the stack before alignment, before aligning, and then we align the thing to the arguments. Yeah, not like this. Oh yeah, args dot alignment. Yeah, and then we know the amount of padding that we added. Stack after aligning minus stack before aligning. Yeah, we call args.compile. Yeah, bytecode instruction.call. And then we have this. Mine is called args size plus expression size. Yes, and then we also need bytecode instruction dot top below top, where we skip the call dot expression size, and we want to pop the padding that we added before. Cool. Align to. Let's make this return padding, and then things get a little bit easier, I think. Okay, and then down here we can just say padding is that. Align to, I mean, sure. Yeah, this is the padding. Okay, nice. Because now if the if the argument of a call requires a greater alignment than the actual return value of the call, then our caller, basically our parent expression, which may be okay, you know what? Let's actually construct something for that, and then I think I'm gonna stop for today, because like this is really cool. But it's also like very mentally tiring, or like it requires a lot of attention, and it is not something, it is unlike anything I've programmed. So, okay, I want to do something, basically have a function that accepts I don't know, a struct, something with size 9, let's say, alignment 8, but it returns something with size 1, alignment 1. You know what, we can't even, let's say alignment 2, it doesn't really make sense. Like, we don't support that actually, but still that should work. Okay, so let's see. Yeah, fun builder is waffle fun builder. Yeah, size 9, alignment 8 is the argument. And then here we have the body that does something, like, I don't really care, to be honest. I guess let's just say it returns a single byte, just hard-coded to return this byte. Ooh, like this, nope, this, yeah. Just returns 42. Okay, and for some reason that has to be a, oh, hang on, we can't even, like, we can't create such a thing. But hang on, can we, let's say we have waffle, how's waffle byte implemented again? Yeah, let's just do something completely custom there. Yeah, currently it's not possible to create something like this, but we want a byte that is aligned to two bytes. Doesn't really make sense. I think it makes sense to require that the size, that the alignment requirement cannot be greater than the size, and also, yeah. Anyways, B is supposed to call A, but first it's gonna push something. Like, create a local variable. It's builder.local. It just creates a byte, 5. And then it calls the A function with, waffle struct or something. And this is supposed to return the size and alignment. And yeah, it needs to return a struct. Waffle struct. What kind of struct? Well, a waffle. A struct with 2 fields, I think. A word. I don't know. 3. And a byte. Let's say group. Let's say group, yeah. Nice. And then that gets called with this, 9-byte alignment of 8 struct. Yeah, and that's basically it. Then we just return some garbage. Let's say just a waffle. We return foo. Why not? I'll let waffle, I don't know, word. 9. I don't know. Okay. Now, first let's check this. Okay, so A returns 42, a byte with size 1, but it has this weird alignment requirement of 2. Great. Then here we have B, which first creates a byte, and then it calls A with this struct. A struct containing a 3, which is a word, and the 1 from above, that is a byte. And this entire struct of arguments has the size 9, alignment 8. It calls that, and the result is, nope, this should be 2. Hang on. Waffle call. Yeah, we don't do this. Okay, and maybe also to make sure that it makes sense to, like, let's maybe put that in a struct that we then return. Basically a struct that contains the result of this call. Yeah, and maybe 2 waffle bytes. 1 and 2, and then the call, which should be aligned to 2. So, okay, well, this is basically unreadable. But we have the first byte in struct, second byte in struct, and then the third byte in the struct must be aligned to 2, because that's the result of this call with that weird alignment requirement. And the argument has size 9, alignment requirement 8. And this entire struct that this function returns, again, has size 3, alignment 2. Perfect. Okay, so first thing here, pretty easy. We push, oh, interesting. Yeah, because we accept something of size 9, alignment 8, we need to push 1 padding to make sure we are aligned to 2. Then we can push the byte, and then we can pop the padding below. Sure, and then the arguments, basically. Yeah, that makes sense. And then we return. Okay, so this returns the byte. Now the next function. This is gonna be interesting. We push the byte 5. Oh yeah, here. Oh yeah, then we want to create the struct with alignment 2. So currently we push the single byte, so we need to push 1 byte of padding to be aligned to 2, and then we push the struct fields. First the 1, and then the 2, right here. And now we want to make a call. But turns out, to call this function, we need to pass arguments that are aligned to 8. So we have, hang on, we have 1 byte, 1 padding, then 2 more bytes. So we need to push 4 more bytes to be aligned to 8. Then we construct the arguments to the call, like the 3 and this tag, this 8. Oh yeah, that was somewhere, basically this one. And then we call that. Okay. But then we haven't yet created our struct, because now the struct has this 1, this 2, then it has 4 bytes of padding, and then it has this byte that was returned from here. So we pop the 4 bytes of padding, basically moving that byte to the rest of the struct. And then to return that struct, we pop the 2 bytes of the local variable and the padding. Sorry, here, the local variable and the padding. Yo, that is amazing. That is pretty amazing. Damn. And surprisingly complex, to be honest. Surprisingly complex. Now maybe I should have gone through that and like drawn a little thingy. I can still do that. Just to have that, you know, documented somewhere. Okay, so we have a function that expects something with size 9, alignment 8. And it returns something with size 1, alignment 2. And then in here, we push a local byte. So our stack looks like this. Then we push 1 byte of padding. I'm just going to put an A in there, I don't know, or P for padding, yeah. Then we push bytes 1 and 2. This byte for padding because we want to build this struct with alignment requirement of 2. So this is going to be the struct. It starts here. Yeah, we push the 1, we push the 2, and then we push 4 bytes of padding. Yeah. So now these are 8 bytes. And this is basically the call argument. So here we make a call. Like we want to make a call to this first function A, which has alignment requirements of 8 for the argument. Yeah, so yeah, we basically just we have pushed padding. Now we push a 3 and like probably gonna look like this, 8 bytes representing the 3, then 1 byte representing from further back on the stack from this 15 bytes. Let's check 8, 9, 10, 11, 12, 13, 14, 15. Yeah, and then we have this. Amazing. Yeah. Then this function is going to return a single byte. So basically it's going to return, boom, we have called something. And then we want to finish building the struct. So we keep 1 byte at the top. We pop the 4 bytes below, boom, and now we have the struct. And then we keep the top 3 bytes here, and we pop the 2 below, boom, like this. And then this function returns. So it successfully built this struct. Nice. Okay. Whew, that was some crazy complicated thing. Like, you know, looking back, it's actually, I think it's not too bad. Well, yeah, but still. Ooh, actually I like the common syntax, yeah. There's a push padding something. That is so cool. So cool. Yeah, I do want to adjust the emit thing a bit. So waffle. That was in here. Waffle to byte. Yeah. And basically, if the instruction is a no op, so if instruction dot if instruction is push padding, and if the amount is 0, then I'm just going to return. And also if we pop nothing, basically, so if instruction is pop an amount and the amount is 0, then we also return. And if the instruction is pop below top, we pop 0 bytes, then we also return. Amazing. This is pretty amazing. Oh yeah, true. Noise. So nice. Okay. Yeah, I think that's it for today. My mental capacity is exhausted. So I guess see you next time.